And welcome back. Now let's talk about number representations. What can we do with representations of numbers? Well, we can do everything you can do you understand in decimal. You can add them, subtract them, multiply, divide, compare them. For example, and by the way, this is a representation in binary. How could we do some addition? Here's 10, 1010 is 10, so 1010 is 10, remember that, memorize that guy. And let's add that together to 7, 7 is 0111. Well, let's do it together. Let's actually do it as we did. You're back in first grade. 0 plus 1, 1. By the way, the maximum value in any of those slots is a 1 in binary. By the way, these are all base 2. Okay, this is base 2 and base 2. 0 plus 1, 1. 1 plus 1, ready? It's 2, which means 0, carry the 1, because it kind of the 1 bubbled over. 2 in binary is 1, 0. 1 plus 0 plus 1 is 2. 0 plus 1 carries. 1 plus 1 there, again, 2, 0, and the 1 carries to here, and you get 1, 0, 0, 1. So 10 plus 7 is 17. And this, ladies and gentlemen, is 17, because that's 16 plus a 1. Now, if I only had 4 bits to do this, I wouldn't have had enough room to store that number. We're going to see that a little later, but that's an important piece of that. So anyway, the point is I just did a simple binary addition, very, very easy. Subtraction, just as you did before, and how do you tell if a number is bigger, if x, some number of binary number is bigger than the other one? Think about that. Is it the total length? What if they're the same length? Let's think about how you test if one number is bigger than the other with this representation. Remember, binary bit patterns are simply representations of numbers. Numbers are a theoretical concept. The value pi, theoretical concept, okay? The numerals are the representations of that. So 123, a nice example, is a number. It's in my head. 1, 2, 3, the way we write it down, so 123, this kind of concept of 123 things, that could be tally marks, that can be anything. That's the number. The concept is a number. The representation is a numeral. Digits are always digits of numerals. You don't have digits of numbers. If you ever say it's a digit of a number, that's wrong. It's a digit of a numeral. Numerals are the written representation of that theoretical concept of a number. So it's the idea of abstraction, okay? Concept, representation of that beautiful idea. Numbers really have an infinite number of digits. We know that. Numerals. I just did it. That's funny, right? See how I did that? Number? Numerals really have an infinite number of digits. Normally, the beginning always is zeros. We'll talk about how, if the beginning is ones, what that means and other things, except for a few of the rightmost digits. So mostly the actions in the lower end up, because it's infinite, so obviously lots of zeros at the leading. We just don't normally show the leading digits there. If the result cannot be stored in the number of bits we have to allocate that, we call that overflow. So here's an unsigned, remember that what we've seen so far is just always positive numbers, non-negative numbers, I'll say. So if I go to 0, and I'm counting, I'm going to use 5 bits. So 5 bits, I can think. 5 bits is 0 through 31. So the smallest number is 0. The biggest number is all ones, is my 31. If I add one more to that, it's going to wrap, and only had 5 bits. It's going to wrap around to 0. We call this overflow. Okay, you might not have heard that before. If I am subtracting numbers and I'm at 2, here I'm at 2, I'm at 1, I'm at 0, and I subtract one more, it'll actually wrap around this way too. It'll go back to all ones. That is not underflow. That is also overflow. People often call it negative overflow. It's not underflow. We'll talk about underflow is in about 3 lectures. So that's if it's too big, okay? Bink. How do you represent negative numbers, though? So far, all we've seen is unsigned numbers. And by the way, if you've ever seen in C, this is called an unsigned integer, or U for unsigned, int. This n is going to be a number 8, 16, 32, which tells you actually the width of it, because this is ambiguous. How many bits is an unsigned int? It's ambiguous. So we started in C99, which they've introduced in subsequent versions of C, now up to C18. We call them U int with a number there, underscore t. That's the type for that. So you should use that. It's called int types.h. We'll get that when we talk about C later. So far we know unsigned numbers. Starts at 0 and goes up. Well, how do we do a negative number? There are numbers on the number line. There are numbers over here. It'd be nice to be able to represent those at some point. Of course, if you owed money, maybe, no, don't represent those at all. That'd be good not to represent those because I owe money. So one way to think about it is let's actually borrow some space from it. So I got 5 bits. Let's borrow a bit. Let me tell you my story. So there's a story I need to tell you here just to put a context to this. There was a rich kingdom, and he had 3 wise people, 3 wise thinkers. And he said to the wise thinkers, I want you to teach me all there is to know about economics. And they went away, scurried away, and they came back a year later, 5 tomes they had written. This is all we understand of economics. We've searched the world. This is the world's knowledge of economics. The king says, no time, no time. Make it shorter. Go back and make it shorter. They came back. We created this single book. No time, sends them away. Another year comes back. We have this pulp fiction novel to explain economics. No time. No. They come back next year. We created this comic book, graphic novel, 10 pages. Nope, no time. We created a single sheet of paper, executive summary. No time. Comes back. So they get grayer and older, and the beards and the hair. They come back. He says, Sire, King, we have come up with the theory of economics in 4 words. And how it became English earlier. He says, yes, go ahead, I have time for that. Ain't no free lunch. What it means is you can't get something for nothing. If you want to be able to now represent negative numbers, you got to give something, you got to lose some numbers that you used to be able to represent, now you won't be able to represent them anymore. So if we borrow a bit, now we can't go as high and positive, but now we can do negatives. So here's the idea. The leftmost bit is going to be my sign. Okay, so you look at that leftmost bit, that's positive or negative, 0 is by the way, it'd be really nice if in all these representations, all zeros were 0. Okay? So all zeros this. That way, when the first bit is 0, nothing changes. Now the biggest number I can represent is 15. Before it was 31 before. But this allows me to represent the negative space. This is now negative 0, negative 0, negative 1, etc. So now, I'm going to show you this way of thinking about this. This is a binary odometer. Back in your olden days of driving an old car that had an analog odometer, the mileage reading, as you go from all zeros, you get a brand new car, all zeros, and you start to drive it, it'll go all zeros. Let's say it's binary. Then all zeros and 1. Then all zeros 1 0. Then all zeros 1 0 0, etc. By the way, I want you to be able to think about counting in binary. See this binary odometer? Your hand can be this binary odometer. Watch this. Here we go. Okay? All zeros. Repeat after me. Try this at home. Okay? This is zeros. This is as you see it, this is the 1 spot, 2 spot, 4 spot, 8 spot, 16 spot. Let's count. 0, 1, 2, 3, 4. I have to block it, see, otherwise I'm on YouTube. 5. Okay, that's 5. 6, 7. This is harder. 8, 9. Let's see. 8. This is harder because I hit 9. Okay, go it. 10, 11, 12. 12, 13, 14, 15, cool, right? 16, 17, 17, dude, okay? Etc., 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 31. Isn't that neat? So what you just saw in this binary odometer, you can do with your hand, and I encourage you to memorize how to do that. 0, 1, 2, 3. That's pretty cool. Do that as fast as you can, see how we can do it. And maybe you're more dexterous than I am. I can't get the 8s up there so well. So, notice that the odometer is good. It starts at the beginning and goes up. Continuous. Nice. As the binary odometer goes up, the number gets bigger. Kind of makes sense. However, watch what happens to the binary odometer with sign magnitude. Okay, that's good. Oh, wait. Now as the odometer is going up, I'm counting and going away from 0 the wrong way. I'm going positive, 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 and then I go negative. That's hard. We don't like that so much. Pennsylvania always went the same way, always went bigger. So think about that as one of the problems with sign magnitude. So another problem, so that was one problem, is this went a weird direction. The second is to build circuitry around this is actually hard because you got to deal with the fact that it's positive or negative, and what if one's positive, one's negative? Hard, okay, annoying. You got two zeros, that's annoying. Does that mean for programming, is it equal to one of those? You have to check for two patterns of a zero now? That's annoying. I mentioned the binary odometer does this weird thing. So actually we don't really use sign magnitude except for in rare cases, often in signal processing. Let's try it again. How about if we just flip the bits? Let's just try, it's another attempt. These are all people sitting with a whiteboard thinking, let's try flipping all the bits when it's negative. So here, let's try it again. So 7 is 2 zeros and 3 ones, okay? What would negative 7 be? Flip the bits. Now, 1, 1, 0, 0, 0, there's minus 7. I get it. So in a way, it actually looks like that leading zero. Look at this. I got the same kind of nice thing is positive numbers have leading zeros. Here's the leading zeros. Negatives have leading ones, but it's not sign magnitude. What's minus 0, 0, 0? Well, all ones. So I still have this problem that there's 2 zeros. We see that already. How many positive numbers? Okay, ask yourself how many positive numbers and how many negative numbers you might have in n bits. Okay, so, but the problem, you see how the problem is? Let's look at the odometer just to see. Ready? Here's the odometer. You go up, and then, if you notice, all ones is at the far side on the left. So actually, as the odometer goes up, after 0, 0, 0, 1, 1, 1, 1, and it wraps to the next number, it's kind of like back in the day of, you have all 0 and all 9s, it wraps to 1 and all zeros in decimal. Odometer is now fixed, but there's still overlap. So you're thinking, well, couldn't we do mostly this, but just take this bottom, here's what we want to do, right? Take this bottom guy and just shift it left. Then you wouldn't have the overlap and it would all work out. And in fact, that's what we do. So the shortcoming, arithmetic is complicated, still got the 2 zeros, although we got the nice odometer to do the right thing, okay? So historically, it was used for a while and then eventually abandoned because this next one is better. We'll teach you what the next one is on the next lecture. We'll see you there.